So yesterday we looked at one subcategory of extrinsic semiconductors, which was n-type. So extrinsic semiconductors are semiconductors where you introduce some sort of impurity or doping. In that, yesterday we looked at n-type, where you introduce a pentavalent impurity. So the impurity atom which you introduce is going to have 5 electrons in its outermost orbit. Today we are going to look at p-type. So in p-type, you introduce a trivalent impurity. So an element which has 3 electrons in its outermost orbit. So when a trivalent impurity atom is doped into an intrinsic semiconductor, it creates a vacancy because again you have the normal lattice structure of tetravalent atoms, let's say silicon, and then we remove one silicon atom and we replace it with something like aluminium, for example, which has 3 electrons in the outermost orbit. Now a normal silicon atom needs 4 electrons in the outermost orbit in order to complete the octet. So every silicon atom enters a covalent bond with 4 adjacent silicon atoms. Now if you take this silicon atom here to the extreme right, it has entered bonds with 3 atoms, up, down and right. To its left, it needed a silicon atom, but it does because there is an aluminium or some other trivalent element there. There are only 3 electrons which it is always sharing, so it is not able to share a 4th electron with this atom. So there is one hole created here without creating an electron in the conduction band. So in order to fill this gap, the electron in a bond elsewhere has to be freed and moved into this vacancy. So how a p-type semiconductor works is you remove one silicon atom and you introduce a trivalent impurity. So there are only 3 electrons. In order to account for the 4th electron, one electron from elsewhere in the valence band itself will be removed and placed in this gap. So from wherever the electron was removed, at that place a hole is created without a corresponding electron in the conduction band. So in yesterday's example we send electrons to the conduction band and we have ionized donor atoms, but we don't have a hole. So here the exact opposite is happening. We have holes in the valence band, but we do not have an electron in the conduction band. So this trivalent impurity, because it accepts an electron, the average energy level is called EA or acceptor. These electrons are, first of all, they are called acceptor atoms, and their energy level is called EA or energy level of an acceptor. Yesterday's case it was donor in n-type, in p-type it is called an acceptor. And because this electron from the valence band, it moves into this vacancy. So again the energy required is very less. It is 0.01 to 0.04 electron volts. So obviously we can understand that this energy level EA lies very close to the valence band. Again, if you compare with n-type, we had ED, energy level of the donor, and that lay closer to the conduction band. Now the energy level of an acceptor, on the other hand, lies very close to the valence band, and the gap between them being around 0.01 to 0.04 electron volts. So and at lower temperatures, electrons of the host is the material your semiconductor is made up of, silicon or whatever. So they acquire the small energy difference required. So your silicon electrons, they acquire 0.01 to 0.04 electron volts of energy, and they move into the acceptor level. They move into the trivalent atoms orbit to fill the vacancy there, hence creating holes in the valence band. So at low temperatures, the number of charge carriers is equal to the number of holes in the valence band, which is again equal to the number of ionized impurity atoms. What are the ionized atoms here? They are the trivalent atoms of aluminium or whatever. Because they get one extra electron, they have a negative charge. So that is the ion being created. So that is the ion being created here. And as temperatures become higher and higher, once all the aluminium atoms have been ionized, then again thermally generated electron hole pairs come into play, and your semiconductor starts behaving like an intrinsic semiconductor. This was again what we studied in the case of n-type also. In the n-type, first your donor atoms will each contribute one electron to the conduction band. Once all the donor atoms have been ionized, the material starts behaving like a normal intrinsic semiconductor, where the silicon loses an electron and a corresponding hole is created. Similarly, in the case of p-type, initially the electrons occupy the spaces in the donor atom, so a hole and an ionized atom are formed without any corresponding electrons in the conduction band. Once all the donor or impurity atoms have been ionized, again this also starts behaving like an intrinsic semiconductor with electron hole pairs being created.